Today, like I said, we are talking about multiplying powers. And I want to make sure we're being very clear in our language here, because we're not multiplying the exponents. We're multiplying the entire power. Remember, the power is the base and the exponent when they're combined. So we're multiplying the whole power. We're not multiplying exponents. Keep that in mind, or you're going to get yourself confused later. And when we multiply powers, particularly ones where the base is the same in each power, it makes the expression much simpler. And that's what we're going after. So before we do that, I want to bring up the term expanded notation. Last class, we talked about scientific notation. They're not the same things. They do have the same ending word. This is different. Anybody want to take a guess, maybe just from the way the term is written, or maybe you've heard it before, what expanded notation is for?
Something to be expanded or like spread out, like you take a equation and like separate it into bits, maybe.
Yeah, a very good explanation, actually. So all this means is that you expand the way that you've written the problem. It's really a fairly, it really does mean what it says. Notation just means a way to write things, and expanded means you make it bigger. So if you were going to write 2 cubed right here, 2 to the 3rd power, instead, in expanded notation, you would write each of the 2's multiplied by each other. So you write the same number of 2's multiplied together as the exponent indicates that you would, right? 2 times 2 times 2, 3 2's. And it's the same way with variables. If you had a to the 5th and you expanded it, you would have 5 a's multiplied one to the next to the next. And you can do the same thing if you have a multiplication problem where you write all of your first bases next to each other and then all of the next set of bases next to each other. And those, of course, are multiplied together because you're multiplying the powers. And so when you're multiplying the powers, you're multiplying all the bits that those powers express. And if you wrote it as a division problem, same thing. You just, all the ones that were in the numerator stay in the numerator, and all the ones that were in the denominator stay in the denominator. So you can see from the colors where everything came from. And it is more time consuming to write it this way, but it can also let us see more clearly what's really going on in a problem. So we're going to be using expanded notation all throughout the lesson, and this is what we're trying to do with it. So let's start off. We're going to start with just positive exponents, and then we'll make things more complicated as we go with throwing in some other stuff. But let's just start with a positive exponent problem. So we're going to use expanded notation. And if we started with this problem, 2 to the 3rd times a to the 5th times 2 to the 2nd times a, if we put it into expanded notation, it would look like this. So you can see we have our 3 2's and our 5 a's times our 2 2's and our 1 a. Right? We have the same number of 2's as the exponent requires. They all line up. Now we can rewrite this, though. We could write this in a way that's more useful to us. And what I'd like you to think about as an analogy is when we're doing algebra, one of the steps that we always talk about is combining like terms. And especially when you have a lot of terms, one of the steps that can be useful before you actually add or subtract them from each other is to write them next to each other. So you can clearly see that, oh, I have all of my x terms here, all the terms with x variables are here, and then all my constants over here. And then I can more easily do the math. And we're going to try that here too. So now we've written our bases all clustered together. So all of the 2's are first now, and all of the a's come next. And you can see from the colors where those came from, right? So we haven't lost anything. We haven't gained anything. We just rearranged it. And we can do that because this is multiplication and it doesn't matter what order they're written in. And the question is, how is this going to help us? This is a lot of work rewriting stuff. Why are we bothering to do this? How is it helpful? And here's why. Now I can say, well, let's count our 2's. 1, 2, 3, 4, 5. Oh, look, 2 to the 5th. 1, 2, 3, 4, 5, 6 a's, 2 to the 6th. So now I just have to count the number of times I am multiplying that base by itself And that's my exponent, because remember, the exponent is what tells us to repeatedly multiply the base by itself a given number of times. Okay, so if we try to put all that together and we run it all together as a problem, it would look like this. And this is without expanded notation. So we get to this middle step where we've written the like bases next to each other. And then we get to our answer. Now, do keep in mind, you can evaluate 2 to the 5th power either in your head, maybe by paper, using a calculator, but that you actually can evaluate. You can't simplify a to the 6th. You don't know what a is, but you can simplify this. So 2 to the 5th is 32. So now I've circled a couple parts of this, and there is a pattern going on here. And there's kind of a relationship here between the numbers that you're seeing. And I don't know if anybody's seeing it. If somebody thinks they see a pattern, I'd love to get their feedback. Does anybody think they see something jumping out at you?
It's adding the exponents on when it comes to the 2, like it's adding the to the 3 and to the 2.
Yeah,
Good.
I was gonna say that. I was gonna say that both of the exponents are added together.
Good. So you're seeing the same thing. And you notice that that's happening with the variables too, right, Ethan?
Yeah.
Yeah. So what's the exponent on that a that's by its that red a?
The one, sorry,
So our red a doesn't have an exponent. What is the exponent, Ethan? If you were going to give it an exponent, what would you write in the, up above it?
Maybe 1.
Right, it would be a
because
1.
It doesn't have anything.
Right, because anything without an exponent, I mean, anything that has an exponent of 1 is itself, so we just don't bother to write it, right? So this is what this could look like then. This is what you guys just described to me, that you're adding the exponents. And the reason I wanted to draw your attention to what's the exponent on the red a here is that I want to be very clear that you can't just ignore that because it doesn't have an exponent. It really does have an exponent, but we don't bother to write it. And that exponent is a 1. So you have to be careful about adding that 1 to the other 5. And then it was the 3 plus 2. And that gets us to the same answer both ways. All right. Does anybody have a question or something they're wondering about at this point? Okay, I'm going to go on because we need to make this a little more complicated. There's some stuff we don't know how to do yet. We started with positive exponents. So now we need to ask, well, what happens if there are negative exponents in the mix? If I incorporate negative exponents, what happens? So we're going to use expanded notation again, and we're going to start with something that looks very similar, but you'll notice some of those exponents are now negative where before they were positive. And now because we made the exponent on the red a negative, we have to write it. Right now it's visible where before it was simply implied. So now if we expand it, and this is maybe going to look a little bit odd, but it's okay. Now I don't have all 2s anymore, and I don't have all a's. All of those 2 to the negative 1s that make up my 2 to the negative 3 are written as 1/2, because I know that 2 to the negative 1 equals 1/2. And I know that a to the negative 1 equals 1 over a. Remember, that's those reciprocals that we were talking about that you reviewed in homework a little bit earlier. So I've replaced all my negatives with these reciprocals. And I still have them clustered like I did before, all of the first term and then all the second term. So we asked this question before, and we were able to kind of move things around. So how could we rewrite things this time? Chloe, what do you think? Do you have an idea about how we could rewrite this that could be helpful? I'm not sure if Chloe can hear me. Hey, Diana, do you have a thought on this?
I'm not really sure.
You're not sure? Okay. Well, if you recall last time when we got to this point, we wanted to put like things together. Remember, we kind of were taking an analogy to combining like terms. And the first thing you want to do to make that easier is to put things near each other that you want to combine. Right. So what we can do then is write it like this. So now all the things that originally had a base of 2 are in front. It's the same thing we did last time. And all the things that have a base of A are clustered at the end. And that's the same thing we did last time. The thing that's different is now some of these are expressed as the reciprocals and some of them are just the base, written as you would expect to see it to the first power. So now check this out. Hey, Diana, maybe you can help me with this part then. If I multiply those 4 things in the box together, what do I get?
1 times 1 is 1. So would you get 5? No, 7. Wait.
So I liked where you were going first. You were talking about 1 times 1.
You would get 8 for the top row.
No, just what's in this box here. So 1 times 1 is 1, times 2 is 2, times 2 is 4, right?
Mhm.
And then on the bottom, it's 2 times 2.
Yeah.
So I would still get 4. So 4 over 4 is 1. So really, if you think about it, this 2 up here can cancel out this 2 down here, and this 2 over here can cancel this 2 over here, right? So everything on the top and bottom here cancels. And that's very convenient because now I can start eliminating things from all of my terms. So those can, these can actually just go away. And the same thing we can do with our variables, because look here at the end. If I multiply A and 1 over A, I end up with A over A, and A divided by A is 1. So that can now go away. Now, how does this help us? Is there a step that we can see to take next? Griffin, do you have an idea on this one? What maybe the next step we could take is? How can this help us, what we've just done?
It kind of makes it a little bit simpler because there's not as much stuff.
Okay. So what stuff do you see that's left?
Just the 1/2 and those 4 A's.
So if you wanted to write that, how do you think you would go about writing it?
I'm not quite sure. I think I would do 1/2 times A times A times A times A.
Okay, you could absolutely do it that way. And I like that method. The other way that you could do it is you could make it look like this, which is kind of the same as what you just said, right?
Yeah.
Right, so we've just multiplied all of these A's by the 1 on top of the half, because of course, if you wrote these A's as improper fractions, they would all have 1s down below them, right? And so we end up with those 4 A's still on top and the 2 on the bottom, because that's all we had left after we canceled everything out. Well, we did have a 1, but I think we can safely not write that here, right? That's not necessary. So that means I have 4 A's, 1, 2, 3, 4. My base is multiplied by itself 4 times, so my exponent has to be 4. And that's the final answer. A to the 4th over 2. So let's put this together again, kind of like we did last time. We'll start from our problem. So could we figure out what each power is by itself and then multiply, or does that mix it up? So I think you're asking, like, could we just evaluate the 2 to the -3rd and evaluate the 2 squared and then go from there instead of treating them as powers that are multiplying together? And you can do that when the base is a constant. When the base is a number, you can evaluate it and then work with the number. You can't do that, however, when the base is a variable. So that variable A as a base, you have to be able to work with it without being able to really evaluate what its value is. I don't know if that answers your question, Cheyenne. And I am waiting to evaluate those because I want you to see the steps that are going on, because the process of why this works is important. All right, so I've written them next to each other, and this is basically what you saw in that when we rewrote in this middle step. And this is just expressed if you just reordered and clustered your exponential terms, your powers. So I've rewritten it again because we know that 2 to the negative 1 is 1/2, and I have 3, it's multiplied by itself 3 times, right? We saw that up at the top. So I've got my base of 2 clustered together and my base of A clustered together. And that gets me to my answer. So thinking about what you're seeing here and thinking about what we saw on the last slide, is there a pattern that maybe you guys are seeing or a relationship anybody is noticing?
I don't know if this is exactly a pattern, but on the, wait, I thought I realized something, but it doesn't work. Never mind.
What, can you tell me what you were thinking and maybe we can talk about it in a minute?
Oh, so I thought like the exponents on top, you could be able to like I was mostly thinking this because you know where it says like a to the power of 5 and it says a to negative 1 and our answer had an a to the power of 4. So I thought maybe they were adding like the exponents together if we would have had the same variable.
Ah, you are absolutely correct. Because isn't that what we did last time? That we added our exponents?
I just got confused a little bit because it doesn't really work for oh, I guess you can simplify it out. I feel like, yeah, I'm just
Well,
confusing.
so let's talk about the when the base is A, because that's what you were just mentioning. The first one has an exponent of 5 and the second one has an exponent of -1. And if I add my exponents, I get 5 plus a -1, which is 4, which is what you were just mentioning. But you seem a little concerned about whether it works for when the base is 2. But on my other set here, I have 2 to the -3rd and 2 to the 2nd, and -3 plus 2 is -1. Well, 2 to the -1 is 1/2. And so really it looks like this. Right? You absolutely are right. It's the same pattern we saw before. It's just that this time we end up with a negative exponent and then we have to do something about it. So if we had, like Cheyenne was wondering, if we had dealt with the 2's up front and we had said 2 to the -3rd is 1/8 and 2 squared is 4, 4 times 1/8 is 1/2, you could certainly have done that. You would have ended up with 1/2, right? And in fact, I would recommend when you're working problems that you do deal with the coefficients just as numbers, right? You apply the exponent, you figure out in the calculator what it's going to be, but do understand that variables you have to be able to figure out using this kind of a method that we're talking about right now. So I had a request for the link to the slideshow, and that's going in the chat right now for anybody who is interested. Okay, so we need to capture some notes about the stuff that we've been talking about, okay? And so if you have some paper with you right now, which hopefully you do, because it's that kind of a class, I'd like you to pull it out and we're going to capture the notes that we've gone over so far so you can see what will be useful later, right? Because we're not going to copy down everything, but we're going to write down parts of what we've been talking about. And that would be a chance where if something we went over the first time didn't quite click for you, this would be a good chance to ask a question. So I'm going to shift over to my document camera. If you have your paper out right now, in the top right-hand corner where we normally put our title, you should write multiplying powers. Now, hopefully it's making a little more sense why I said we're not multiplying exponents, right? Because we're actually adding exponents when we multiply powers. Right? So we're multiplying powers. That's what we're doing today. That's our purpose, to figure out how to do that. And I just want you to start off by writing the words expanded notation, because I want you to remember that that is how we've been starting all of this, and that's the term that we use for what this is. And I'm going to write down that problem we were using. And the one we did when we had positive exponents was 2 to the third and then a to the fifth times 2 to the second times a. And you recall we expanded it, and we're going to write parts of this out. 2 times 2 times 2. And I know there's going to be a lot of a's, but just hang in there with it. So that's my first term, times 2 times 2, and at least they're less in this second one. Okay, and then this and this are going to get written next to each other. So we're going to write 2 times 2 times 2 times 2 times 2, right? So there's 2 and there's 3. And then we're going to multiply a times a times a times a times a. And that was 5 from the first, and there's our other a. Right? You can see where things came from. You can add the arrows. Sorry, I made my arrow too long. You can add the arrows or not as you choose. Okay. And now we can count them up, and we could say 1, 2, 3, 4, 5. The base is multiplied by itself 5 times. So I get 2 to the fifth. 1, 2, 3, 4, 5, 6. The base is multiplied by itself 6 times. I get a to the sixth. When I combine those, I get 2 to the fifth, a to the sixth. I know I can evaluate this first one where the base is a constant, and I just happen to know that that's 32. You might use a calculator. You could write it out however you want, a to the sixth. But then the pattern we talked about, the pattern was, and I'm going to write it again, and we're going to see what it would look like if you did it the other way. And I had students earlier who were saying that they really found themselves using some of both of these techniques. You know, part of the time they were using this method where we're just adding, and part of the time they realized that considering things in expanded notation was also very helpful. So don't feel like you're limited to one or the other. And I'm going to add that exponent of 1 here, right? So that it's a little more explicit that it exists. And now we get 2 to the third times 2 to the second times a to the fifth times a to the first, which you can rewrite 2 to the 3 plus 2 times a to the 5 plus 1.
Mrs. Flood, it's a little tough to read that the exponents there under the patterns.
Okay.
Yes.
And let me brighten it up a little bit. That might help some too. Did that make it any easier to read?
That does a little bit. Mhm.
Okay. All right. Thank you for letting me know, Mr. Warhol. And guys, if you're having any trouble reading, please do say something. I can adjust things on my end. Right? You don't just have to suffer through it. And so we end up with 2 to the fifth times a to the sixth, which we already know from before is 32 a to the sixth. So you could work it either of these two ways. One of them might make more sense to you, or as I said, you might find yourself using elements of both of these as you work through certain problems. You would not be the only student who did it that way. And then I want to capture what it looks like when we have negative exponents, because those honestly give students more difficulty. Those are a little more challenging. So I'm going to move down and start writing about what I'd like you to copy down for negative exponents. So we're going to start with that problem again. So it's 2 to the negative third, a to the fifth, times 2 to the second, a to the negative first, right? So now we have those negative exponents mixed in. I'm going to write this one out with expanded notation, but I'm going to do it a little bit abbreviated. We know that 2 to the negative first is 1/2. So I have 3 1/2 here, and I have my 5 a's times 2 2's and a 1 over a. And just so you can visually represent this to yourself, I'm just going to draw arrows connecting what would cancel other things out when they multiply. right? This 1/2 times this 2 becomes a 1. This 1/2 times this 2 becomes a 1. This A
How
times
did you
that
get
1 over A becomes a 1. I'm sorry, say again?
how did you get the 3 1/2?
So I'll write that over here on the side. 2 to the negative first power equals 1 over 2, right? That's our reciprocal. Does that make sense?
Yeah.
Okay, and this is 2 to the negative third, which is 1/2 times 1/2 times 1/2.
Okay.
Does that make
Would you
sense?
do that with any number?
Sure,
Okay.
sure. So if this was 4 to the negative third, it would be 1/4 times 1/4 times 1/4. If this was 4 instead of 2.
Okay.
But you can see that this 1/2 and this and that, so all of these where the arrows are drawn are effectively canceling each other out because anything times its reciprocal is 1. And so now we're left with, and we'll bring it down, 1/2, because there's just 1/2 left. And I still have 4 of my A's left. And I say 1, 2, 3, 4. A, the base, is multiplied by itself 4 times. So my exponent must be 4. And I have a 2 in the denominator, because remember, multiplying by 1/2 is the same as dividing by 2. Those are equivalent mathematical operations. Right, so it would look like that. If you want to do it this way and think about it this way, that's great. The other way that we talked about, and we're going to use the same problem, and I'll show you with just adding the exponents. So 2 to the negative third times A to the 5th. And if somebody has a question along the way, I really would love to know them. And if you think I'm going too fast and I need to slow down, please let me know that too.
I just have a quick question. Can you
Sure,
kind
go
of
ahead.
explain how the 1/2s cancel out with the 2s?
Okay. Let me just write that over here on the side a minute. So just, and I think you'll see it when I write it visually. I think you'll get it. So if I have 2 times 1/2, 2, if I write it as an improper fraction, would be over 1. Yes?
Yeah.
Okay, because it's 2 1s, it's 2. And now when I multiply across, 2 times 1 is 2. 1 times 2 is 2. 2 divided by 2 equals 1.
Oh, that makes more sense now.
Right, and so as long as you get a 1, you can go, oh, well, anything multiplied by 1, that's kind of, it's just itself, so I can ignore it now. So back to our problem down here. Okay, so that's just the same terms that we had up here. It's the same thing I'm writing again. And now we're going to say 2 to the negative 3 times 2 to the 2, right? We're just reordering them. Just so you can clearly see them next to each other. This becomes 2 to the negative 3 plus 2 times A to the 5 minus 1. Negative 3 plus 2 is negative 1. 5 minus 1 is 4. And I'm left with this. I know 2 to the negative 1 is 1/2 times A to the 4. And I am left with A over 4, the second, which is the same answer we got before. And I don't necessarily expect that you're going to show all of these steps. You may not need all of them. Some of you,
Go
say again?
A bit more.
Can I do which?
Yeah. Just
Okay.
yes, good paper. Yeah. Thanks.
Yep, there you go. I don't necessarily expect that you're going to show every one of these steps when you're doing your work. You certainly could, right? This would be very clean, a very easy way for you to not get lost. If you feel confident enough that you want to skip some of these steps, like you want to go straight from here to here, that's totally fine, right? I would be a little hesitant for you to try and skip straight from the beginning to the end. That's a lot of steps to skip past. That's kind of what you feel comfortable with and what you can get the question right by doing. But I would expect right now I should see at least 1 or 2 steps in between the beginning and the end of the problem. All right, I'm going to switch back over and we're going to talk about one more complication because Every time you learn something about math, there's always one more complication you could learn. But you're definitely going to need to know this because it will be something you're going to be working with in a little bit. And it's just kind of an extension of the patterns that we've already been talking about. So watch for that pattern extension. So the question is, we've talked about positives, we talked about negatives, but if there's a negative exponent in the denominator, is that different? How do we work with that? What does that look like, right? What happens? So we are going to start with the problem. It's a different problem. Now our negative, we have two numbers, two variables in the bottom. One of them has a negative exponent. We're gonna, and sorry, I'm sorry, before I get any further, I just put this up on the side there for you on the right. So as a reminder, as we're going to how we would get all the 1/2 you're about to see. Okay, so that's why that's there. So we're gonna expand this and it's gonna look like this. And so this thing I wrote over here that we know a to the negative first power equals 1/2, that's how we got all 5 of these 1/a terms. Right? It's just the reciprocal. We just talked about that in that last screen. And then of course that a to the first power just stays a. Now look here, we just did something like this, right? We were just talking about this with 2 times 1/2, but now it's a times 1/a, which means it goes to 1 and you can ignore it. So those 2 terms have gone away. Now we're left with this. That's what's remaining after those 2 terms are gone. But fractions in the denominator are messy, and we don't really want to have fractions in the denominator. We don't want a complex fraction. We want something cleaner than that. And we can't just rewrite it as an exponent on the bottom because it would still have a negative exponent. So we got to make those go away. Now, before we managed to make one go away by doing this, does anybody think they have an idea about how you could make those fractions go away in the bottom? Any ideas? So if we multiplied by a once and made one of them go away, what if we kept on multiplying by a until they all went away? Could that work?
Yeah.
Yeah, you think so, Shannon? Ah, Griffin agrees. So here's the only catch on that. If you're going to multiply the bottom by something, Griffin, what else do you have to do?
You have to multiply the top.
Absolutely. So if I'm going to multiply the bottom by a 4 times, I have to multiply the top by a 4 times, right? And then here's that arrow again, like I showed you in the notes, and each of those a's on the bottom will match up with one of those 1/a's, and they'll all go away and become 1. And then your denominator effectively disappears. We just won't bother to write it anymore.
What if you multiply everything by only 1a?
Then only one of the a's would go away, and you would have 5a on the top, and on the bottom you'd still have 1/a times itself 3 times.
Okay.
Okay, so each a can only, like, you can think it only cancel out 1/a term. Does that make sense?
Yeah.
Okay, all right. So you're left with a times itself 4 times, which means that's a to the 4th. And you have a 5 left that just stays there. There's nothing you can do to simplify that. Okay, so let's look at it. If we think about the pattern we've been talking about, right? Could we get to the same place applying the pattern we've been discussing? So we have 5/a times a to the 5th. And then look, if we do our exponents and we add them, right? We had a 1 on the blue one and a -5 on the red one, and we add them together, and we get 5a to the -4th. And we know that a to the -4th, if we bring that up, right, it becomes positive, and it looks like that. Okay, so we're just going to add this last piece here on the bottom into our notes, and then we're going to go play our game, okay? So I'm gonna shift over to the document camera. We're gonna add that, and then we get to go play our game. There we go. So starting up here at the top of the next page, because that's where I got to at least, and wherever you are on your page is cool. I'm going to write that problem. And first I'm going to write so that you can know where to look in your notes later. Negative exponent in the denominator. So this will just kind of be like a landmark when you're trying to find this part later. So a problem we were working with was 5 over a times a to the negative 5th. And what we did was we said, well, that's the same as 5 over a to the 1 minus 5, or you could think plus a negative 5, right? Because really the patterns that we're adding, not that we're subtracting, but we know that adding a negative is the same thing as subtracting a positive. So then we can go to the next step, 5 over a to the negative 4. Right? And we happen to know that a to the negative 4 is equal to 1 over a to the 4. And a to the 4th is equal to 1 over a to the negative 4th. Right? Those are both true statements. And so we can then substitute this one here in here and say 5 times 1 over a to the negative 4th. Now I can substitute here and I get 5 times a to the 4th. And that's why it works. Right? Or you could just think the shorthand is, if I just flip this to the top and change the sign, then I get here, right? That's another way of thinking about it, like we talked about in the homework. Does anybody have a question on that one?
I have a question.
Yeah, please.
So on the second, I don't really know how to explain, but on the second like fraction
Right here?
You did like 1 minus 5. So
Okay.
I think you like took that a and then changed it into a 1, right?
Yes. Yes.
But we didn't like a times 1 just equal a. Like, how does that become 2 a's?
So let me write it this way a minute. If I have a to the first power, what does that equal?
A, right?
Right. And if I had 1 times a to the first power, what does that equal?
A.
Right. And if I had 1 times a to the first over 1, what would that equal?
Oh geez. I'm gonna guess A, I think.
It absolutely is. So really, whenever you see this, just this variable by itself, you could argue that it has a denominator. You could argue that it has a coefficient. You could argue that it has an exponent. We don't bother to write any of them if all of those are 1, right? So whenever you see a variable that doesn't have an exponent, you need to assume that that means that the exponent you can't see is a 1. Just like if I see an A without a coefficient, you know to assume that the coefficient would be a 1 if I was going to bother to write it. Does that make
Okay.
sense?
Yeah.
Yeah. So it's there, just like the coefficient of 1 is there and the denominator of 1 is there, but nobody would bother to write it because it's messy and it wastes time. But you do need to consider it, and you might find it very helpful when you get a problem to go through and anything that doesn't have an exponent, give it an exponent of 1, because then when you're looking at the problem to try and solve it, you'll go, oh, that's right, I need to think about that 1. Otherwise, you run the risk of ignoring it. So I think it's a very good point you raised, and that's something you could do that would help keep you organized, is add a 1, even if it wasn't there in the problem originally. Okay, we're going to get a chance to practice this stuff in a game, and I'm going to pull up the game. I'm going to switch to sharing that screen. And as I said, it's a ball game.